The reason I think nuclear power is important is set in the larger context of what is our energy problem. And I think our energy problem is really based on two things. The first is the world's getting prosperous. Everybody on Earth wants to have the lifestyle that we have in the developed world. You know, most parts of the developed world use between 5,000 to 10,000 watts of power per person. That's all forms of energy, fuel and so forth, as a watt equivalent. The developed world uses maybe a tenth that. China about 1,500 watts per person versus about 10,000 in the United States. So there's a factor of 7 difference. And during this century, that factor of 7 difference is going to go away. Now, maybe not every part of the world will get up to exactly American standards. Maybe they'll make it to European standards, or about half of what the US is. But it's going to be an awful lot of energy. Now, for electricity, that means we have to be thinking about doing at least 4 or 5 times as much electricity generation as we do today. But as we start using electricity for transportation with electric cars or other vehicles, as we start the process of moving to a carbon-free society, we could actually need to build a lot more. Today in the United States, we only use about 1,500 watts per person of electricity. The rest of those watts come as oil, as gas, as coal, in other forms. So to get those non-electrical parts up, we have to increase our electrical generation capacity in the United States by maybe a factor of 7. So you start tossing factors of 7 around, and the world could be in for an enormous amount of energy demand. That's really a very different picture than many people have. They think of the world as being about a static demand and, oh, we'll save a little bit here with conservation, we'll save some here with renewables. In fact, if we have to go from generating, say, a terawatt of electricity right now on the Earth via carbon-intensive forms, to generating 10 terawatts or 50 terawatts in a clean way, we have a problem. And that's the second reason that nuclear is interesting, is that nuclear is a low carbon or zero carbon emission form of baseload power. Baseload's important because most renewable energy sources have the problem that the sun doesn't shine at night and the wind doesn't work when it's still, or actually when it's very windy. So most renewables have a pretty low duty factor or capacity factor. Solar, typically 20%. If you build a gigawatt plant, you can get about 20% of that out, averaged over the year. And that's in Arizona, or a place similar to Arizona. If you go to a less favorable area from a perspective of sun and clouds, it'll be even lower than that. Wind typically is about a 30% capacity factor. What do you do when you don't have the wind blowing or the sunshine? Well, that's when you need baseload power to back it up. Today, that power is typically coal or natural gas. And both of those sources just emit too much carbon. It's this carbon thing that really makes the growth picture complicated, because we don't have any renewable schemes that work in a baseload fashion. We also have some pretty significant cost issues with renewables. So what's the answer? Well, one answer would be a miraculous new technology. A miraculous kind of battery actually would go a long way towards solving some of our problems, because they would let us make power during the day when the sun is out or when the wind is blowing and save it up. Unfortunately, batteries don't work well enough for that today, and there's no prospect in the immediate term to get there. Maybe someone will have an idea, and I think that hopefully a lot of folks are trying. So if you look back and say, well, what does work in a carbon-free baseload fashion? The answer is nuclear. But today's nuclear has got a couple of issues. It has some cost issues. It has some perceived safety issues, some waste issues, and some proliferation issues. So nuclear is great except for all that. How can you surmount that? Well, we and a number of other folks are working on new kinds of nuclear power that try to address each and every one of those problems. So as an example, we can burn waste as fuel. We can take either spent fuel rods from conventional reactors or depleted uranium left over from the enrichment process, again from conventional reactors or even military purposes. And we can take this waste and we can burn it as fuel. Now, that's significant for two reasons. The first is it takes this huge waste problem and solves it by burning it. The second is we have mountains of this waste already. Literally, we were going to put a bunch in a mountain in Nevada till that got stopped. But collectively, the world has so much uranium that could otherwise be used. That also brings us to scalability. You know, conventional nuclear power is limited by the fact that the uranium that you actually burn, U-235, is only 0.7% of natural uranium. The rest is U-238 that you have to separate off, and it becomes waste. In order to scale our energy up by a factor of 5, 10, 50, as we're going to have to do, we're going to need a lot of whatever the power source is. So if you used conventional reactors, you'd run out of uranium. Now, people have known that for a long time, so they've planned on saying, let's use something called a fast reactor or a breeder reactor. They're very complicated and they have a whole variety of their own issues. That's why we came up with our TerraPower reactor, which burns waste as fuel. It's also significantly simpler. We think it's much safer, and it has very reduced proliferation risk. Now, I can't promise you that that's the only approach that will meet that. Our company is also working on a variety of other areas. We're working on trying to improve renewables. We're working on sources of energy that are quite different than nuclear. But nuclear today has got to be part of the mix because it's the only thing that's proven to actually work as a large-scale, carbon-free baseload power source.